So recording has started and then we can begin with. Now before starting, Nikhil, you have doubt with week 3 assignment part B. So can you speak out what exactly your doubt is? Because I think we had covered it. Let me see if I have it ready. This should be assignment 3. I will share my screen and then we can discuss it out. It's still opening. Okay. So before starting, how many of you were there in the last few sessions? I see Nikhil, I think you were there. Do any of you guys were there in the last session or before that? Or are you joining for the first time?
Yeah, this is my first time.
Okay, you are joining it for first time. DB Shantosh
Yes.
Kumar. And what about you? Shailesh Kumar, second time. Okay. Yeah. So anyway, these lectures are already uploaded on YouTube. So if you want to see it later, you can check that out also. Okay. Yeah, it's loading. Okay. Meanwhile, it's loading. What I wanted to discuss was how many of you have access to Aspen right now? So the way I have planned out today's session is that we will be solving multiple property analysis problems. So what I will do, I will solve some problems and then any of you can share your screen and solve it with me. So that way it will be more interactive. Since there are multiple small questions that we can proceed it that way. So how many of you have access with Aspen Plus and can share your screen? Okay, so Santosh Kumar, you can. Anyone else?
Yeah, I'm having.
Yeah, you have Aspen Plus, right? Yeah, okay. It's not responding.
I'm audible.
Yeah, you are audible. Yeah.
I joined to tab and the lab.
You have joined from tab. Okay.
But I having it.
You have
I do my lab.
Aspen, but can you do it? Like if you can share it with. So else if not then I will do it by myself, but I wanted to be it more interactive kind of thing. Anyway, it's okay, we will see. Okay, if you can share, if you can join via your laptop, that will be better. Okay, so just before it starts, let me just briefly introduce myself. So this is the course on Aspen Plus simulation software, and this course is for beginners, right? And uh, obviously course is run by Professor Prabirkumar Saha, and the lectures are uploaded weekly. And I am Bhavesh Moorjani, and another TA Rajdeep is there, Rajdeep Mukherjee. So we are the TAs for this live interaction sessions. So weekly we will have this interaction session. So my session is on Tuesday from 6 to 8 p.m. Okay, and the purpose of this session is to kind of interact with you guys, solve your doubts, do some problems so that you can get more familiar with this Aspen Plus software. This is just brief about me. I'm currently doing Ph.D. at IIT Bombay. I have done my bachelor's from MS University Vadodara, where I was introduced to this Aspen Plus course, and right now I'm TA of this course to help you out with this course. And I think someone's microphone is on. If you can turn it off. Yeah. Okay. And So as I was saying, these are the various ways you can contact me via LinkedIn or email ID. Just wait for few days for my response. If I'm busy, I will respond you to within 1 or 2 days. Okay. Now, so this is the week 5 of our live interaction session, and that will be mainly related to the property analysis part. So before starting that, I think Nikhil had doubt, and it has opened up. So yeah, Nikhil, this is the problem of water methane reaction, the extreme reforming reaction. So I'm not understanding what exactly your doubt is. So if you will speak out, then only I will get to know. Can you please speak it out? Don't worry about being formal. Okay. Yeah, I got your point, but what exactly your query is? Let me open the week 3 assignment 3. So see, you have been given this reaction. So this is steam reforming reaction where methane is reacting with water to form hydrogen and CO. And then you have another reaction, water gas shift reaction, where carbon monoxide is reacting with water to form hydrogen and CO2. Okay. And you have been asked to simulate this via equilibrium reactor. Okay. So model this reaction as an equilibrium reaction using equilibrium reactor in Aspen 14. For this calculation, consider natural gas as poor methane being fed to the reactor at this temperature and pressure condition. Preheated steam condition are given, molar flow rate is given, and reactor is operated at 500 degrees centigrade and 34 bar. Pang-Robinson method is used. So I will just give you an overview what we have done here. So in the property, our components are all the compound which are present in the reaction. So methane, water, CO, CO2 and hydrogen. And the method that we have selected, so Pang-Robinson is specified, so Pang-Robinson method is selected. Right? And in the simulation front, we have used equilibrium model. So it has been said that model this reaction using R equilibrium. Okay. Provide the connection, so your methane and water is coming. So input parameter for that will be provided. So methane temperature, pressure condition, molar flow rate is given. Same for water. Okay. And now for the reactor part, input of the reactor. So temperature, pressure conditions. This 800 I have changed it. I think it was for last question. So that's it, 500 degrees centigrade and 34 bar. 500 degrees centigrade and 34 bar. Reactions are added. So we have added this 2 reaction. One is steam reforming reaction of methane, and second is water gas shift reaction. Okay, since it's equilibrium reaction, we just have to provide the coefficient like stoichiometric coefficient of your reaction. That's it. And when you will run it, you will get your results. Okay. So here you can see the steam results. So you only have a vapor phase coming out from your reactor. And then you can answer the question, volumetric flow rate of methane fed to the reactor. Obviously. So flow rate, volumetric flow rate of the methane. This is in pound per second. So you can change the unit. Pound per second, 48.73. Okay. So the answer is within the range between 47 to 50. The mass flow rate of CO2 in the vapor stream. So in your vapor stream, go to the mass flow. This is your outlet. So mass flow rate of CO2 427 kg per hour. Okay. So that way you can answer other question also, like heat duty of the reactor. So that will be here in the results of the reactor part. This is the heat duty. Okay, 1193. So I guess this will answer your question, right, Nikhil? So this is how you have to solve the assignment question that has been mentioned. Okay. Uh, so I assume your doubt is clear. You're welcome. And I would recommend you guys to speak it out. Again, this is an interaction session, so we have to interact, right? So don't worry. I'm saying again, don't worry about being very formal. If you are not comfortable, you can try to speak it in Hindi also. It's fine. This is just an interaction session, so that your doubts will get solved, and it will be easier for me to understand what you exactly want to understand. Okay, want to know. Now, before beginning, again, there were many students raising the issue of assignment 4 also, that the curve, Gibbs energy curve that was being generated. So people had answered it as U shape, and the correct answer is given as V shape. But I have talked with sir, and he has said that U shape answer will also be uh, given as is a right answer. So people will be given marks for that also. Okay, so you don't have to worry about it. I will post it that on the Q&A form, this Q&A forum. I forgot about it. Okay, so does any of you have any doubt related to the previous stuff? If not, then I can move forward with the today's lecture. Okay, so I guess you don't have any doubt. So let me start today's lecture for. Just a minute. There seems to be some issue. Yeah. Okay. So last week 4 lectures and week 5 lectures, basically we were dealing about how to estimate various properties through Aspen Plus, what kind of method to select, that was suggested in the week 4 part, and the week 5 part is about how to do property analysis of pure component, binary component, or mixture through Aspen Plus. So before starting this thing, I want to understand like why we need to do this property analysis anyway. Let's say we have a compound, so we get to know their property, their density, their vapor pressure, their heat capacity at various temperature pressure condition. But how exactly this is useful? So property analysis is useful, like property of any compound, that is needed for basic preliminary design calculation to detailed design calculation, right? So let's say take an example of heat exchanger here itself. Like if we want to do heat exchanger calculation, what we do, we write that mcp delta T on the shell side will be equal to mcp delta T on the tube side, right? So here what we need, obviously mass flow rate we will have from the process and delta T, but then we need the property of fluid both on the shell side and the tube side to find the desired temperature or the heat duty that will be required for any heat exchanger. So this is a basic example of energy balance where you need property of your compound which is present in the stream. Okay, now this is the basic example. When you will move forward to the designing of various equipments, there you need multiple such compound specific properties, such as vapor liquid equilibrium data in the distillation column. That is also needed to do complete column design, right? So then we need TXY, PXY plots, YX diagram, relative volatility of your compound at different conditions, whether azeotrope is being formed or not. If azeotrope is being formed, what will be the solvents which will that we can use to do an extractive distillation. Okay. So these are the some of the questions which are answered by this property analysis method. So let's try to brainstorm for different unit operations that I have mentioned here, unit operation and processes. What will be the property required? So let's say for heat exchanger, what will be the various properties needed to do complete design of heat exchanger? Can any of you answer it? So one property I have already mentioned, that we need heat capacity of are both hot and cold fluid to do an energy balance. But what about other properties? Can you repeat it? Sorry.
Viscosity of the fluid.
Yeah. So viscosity of the fluid. Then can you think about the detailed design of heat exchanger? Where there what we need is, we also
Velocity
need,
of the fluid.
yeah. So velocity is a system property, but then I'm saying about the steam property. So let's say you have to find the heat transfer coefficient, right? And you have the Cedar-Tace-Little-Booth equation in terms of Reynolds number and Prandtl number. So there you need density of your stream, viscosity also to compute the Reynolds number, right? So density is one property, viscosity is one property, Cp is also one property, heat transfer coefficient is also one property. Similarly, for distillation column design, we need Txy Pxy diagram, right? At various pressure. So we need Txy diagram at various pressure condition to decide how much separation will be possible. That too just for a design of a distillation column. If you want to go for column specific internal design, or to find the, in that case again we will need rho, mu, Cp of the Cp of your fluids. In Ponchon-Savarit we use energy balance calculations also where the Cp will be needed, right? Same goes for the absorber where we need this sort of a parameter. In pump again, what will be the values needed for a pump design? Viscosity, right?
Density of the fluid.
Density of the fluid, viscosity. Same goes for the reactor. In the reactor, if you want to see whether reaction is happening or not, so there we are interested more on the thermodynamical property part, such as let's say Gibbs free energy, which will help us to determine the extent of reaction. We just saw the nickel stout related to the R equilibrium example, right? So similarly, we have this R Gibbs model available in the reactor part model palette. So what does R Gibbs does? It does the Gibbs free energy calculation, and the lowest chemical energy potential, or the Gibbs free energy, will give you the maximum equilibrium or equilibrium composition that can be achieved. So such sort of a properties of any compound, and these are the basic properties. I mean, more than this thing might be needed. I'm just listing out the few stuff which are needed to just kickstart of the calculations. So property analysis becomes crucial, and specifically when we are designing an equipment. So let's say you have some TXY data for distillation column design. Now accuracy of this data, accuracy of this property will also matter a lot, because in the column design itself, like we are talking about the economics. If I have some data which has 10 to 20% deviation from the actual experimental value, and I'm using some properties which gives me deviation from the experimental data, and I design that on the theoretical values itself, then the column might go over design or be under design. If it's under design, it will perform poorly. If it's over designed, then it will be a costly thing, right? For a desired separation, we have made a much higher specification column. So such sort of things are needed to be considered. So that's where this property analysis comes handy. In Aspen Plus, we have different analysis tools. As I was saying that, and you might have seen the Saha's lecture also. This is from his slides only. That we can compute the pure component properties. We can compute PT envelope, binary system, TXY PXY diagram, ternary system, where you might have taken out the ternary diagram for the liquid-liquid extraction. Okay, so that sort of stuff we can do from the Aspen Plus uh, based on the models available. So whether you use Bank-Robinson equation of state model or activity coefficient based model such as Unific or NRTL, there you will get properties of your system based on the equation. But let's say your compound does not have this unifact parameters or NRTL parameters or equation of state parameters. It's an unknown compound. In that case, we might to do some property estimation. That property estimation can be done in Aspen Plus via regression analysis uh, through property estimation tool, either NIST data. This stuff we will discuss it today. Sir has already covered it, so I'm just listing it out, that if you don't have a known compound, in that case is also, in order to do this design or design of your process, we will need that data. So we need to have some measures available to compute it. So these are the various property, if we have to estimate the property for an unknown compound. So these are the various properties that we can estimate via the Aspen Plus. So what Aspen Plus does is that it will use some group contribution method to compute the normal boiling point, critical pressure, temperature, volume, heat capacity, Gibbs energy, enthalpy of vaporization, etc. Okay. So again, I'm not going into the much theoretical detail part of it. Rather, we will just start with some problem solving. Okay. For the regression part, Aspen Plus has some of the libraries already available, which is NIST, TDE, and DCAMA. Sir has already covered it in his lectures. So your compound data might be available in such website itself, or you might have some experimental data which we want to fit in to do other property computations. So there regression will be helpful. Okay. So we will try to cover all such examples today. So let me start with the basic example. So first we will do some property computational analysis, and then we will move towards the regression analysis. Okay. So what I will do, I will solve first question itself, and then any of you, if you want, you can share your screen, and then you can do second problem on your own. That way we will proceed. So first problem is that we have to find the density, specific heat capacity, Gibbs free energy, and PT envelope of thymol. Thymol is a molecule at atmospheric pressure from 10 degree centigrade to 100 degree centigrade. Okay, straightforward, simple calculations. So I want to add a compound. So thymol is a small molecule. It should be directly available. Thymol. Yeah. So thymol is added. Go next. Now it is asking for property method estimation. Now here no method is specified. So let's move forward with the Unifact method right now. So I'm selecting Unifact method. Go next. Run the property analysis. Now once this will run, we will start analyzing various properties. Table generation complete, results are available. Okay, so here you can see on the top toolbar panel, here you have pure, binary, mixture, solubility, and PT envelope. Right now we only have one compound, so that's why binary, mixture, and solubility or ternary diagram, this options are not available. We can only do pure component analysis. If I will add the second component, this binary solubility part will open up, and if I will add more than two, then mixture and ternary diagram will come up as an option. Okay, so right now we want to study the pure component properties. So click on the pure. You will see here under the analysis tab, pure folder has been created where we will provide our properties. Okay, so here you can select different types of property, whether you want to compute a thermodynamic property, you want to compute transport property, which kind of. So this is kind of a filter. So right now we want to compute the density. Okay, so density is a thermodynamic property. So if you will see, there are list of options, and when I will put my mouse on any one of them, I will get its description. So this GIG, it's ideal gas free energy for a pure component. HIG is ideal gas enthalpy for a pure component. If you are confused between this term, you can use the search button also to find out what exactly that property means. Okay, so right now we want to compute the density, so that is rho. Select that. What are the units that you want to do? So let's say I want to see in kg per meter cube, so kg per meter cube. Now here you have option whether you want to see vapor phase, liquid phase, solid phase. So let's select liquid and vapor both, because I don't know right now what will be the exact phase of thymol here. Okay, you on the right hand side you have list of different components available. Select thymol. Pressure value is specified. Find the density at atmospheric pressure. Okay, so 1.01325 bar, that is 1 atmosphere. We can provide the temperature interval start to end point. We have been asked to compute the property between 10 to 100 degree centigrade. So provide 10 to 100 degree centigrade. You can change number of intervals, how many intermediate points you want. Once this all stuff is done, just run the analysis and it will create the plot for density versus temperature. So what will happen with this curve? Like, will it be increasing? Will it be decreasing? What happens to density with temperature? That's a basic question. You should be able to answer it.
Yes.
Yeah, density of your compound will go down, right? Yeah, so you can see we have liquid density of thymol, vapor density of thymol. Liquid density is going down with temperature, and for vapor density, if you want to zoom it in the graph, you can do that and see the change in the values. You can also use cursor, it will point out the values also. Okay, like here. Now let's say you want to save this data. So what you can do in your analysis part itself, if you will go into the result, this data is available. Okay, so with temperature at given pressure, I have liquid density and vapor density. You can select this and copy it out, and then you can paste it in your Word or Notepad. Let's say I'm just putting it in Notepad. Okay, so this is how you can save the data also. So this was the density part. Now I want to compute what other property has been asked is we have been asked to compute Cp, constant heat capacity of pure component. Let's compute it for both vapor and liquid, and let's select this kilocal per mole Kelvin unit, and temperature is 10. Run the analysis. It's running. It will take some time. Okay. Just wait for a minute. So now you have both enthalpy of vapor as well as liquid phase with temperature, how it is changing. So let's say you want to perform some energetic calculations, and then you need you need the data of enthalpy, the CP values, heat capacities values for your thymol compound. Then you can find it from this way. What other things has been asked to us is Gibbs free energy and PT envelope. So let's try and compute Gibbs free energy. That is again a thermodynamic property. So go down, here you can see the free energy of a pure component, that would be unit be joule per kilomole, and I want to compute both for vapor and liquid and run the analysis. It will take some time, please bear with me. So these are the Gibbs free energy of both vapor and liquid thymol with temperature. Now what does this signify? It shows that for a given temperature, Gibbs free energy of liquid is more compared to the vapor, like more negative compared to the vapor. So Gibbs free energy of liquid phase is less than the Gibbs free energy of vapor. That means at given temperature, which phase will be more stable, vapor or liquid?
Vapor.
Sorry, can you repeat it?
Free energy is more in vapor state. So vapor should be still.
No, free energy should be minimized of the system, right? So minimum free energy is in this range, the below. So liquid will be present. So it will thymol at a given temperature would prefer to be in a liquid phase. So what happens in your free energy curve? Like this Gibbs free energy of vapor and liquid, when the crossover happens, that crossover will happen at boiling point. So as you can see, this vapor the slope, if you will see, the vapor phase Gibbs free energy is going this way, and the liquid phase is going slightly up. So they will cross over after some point, let's say after 150 degree centigrade or something. So when the Gibbs free energy of vapor and liquid will be equal, that will be your boiling point, right? So right now you are currently in the liquid phase region of the thymol. So if you want to know the property, like if you are confused between which CP value to select for a given let's say 60 degree centigrade for your calculation at 1 atmosphere, so thymol will be mostly in the liquid phase. Okay, so you will select this value rather than this value. Okay, we can check this out also. Let's say right now we have done calculated values between 0 to 100 degree centigrade. Instead, let's do between 50 and 200 degree centigrade and run the analysis. Can you guys hear this noise coming from outside? I'm sorry, actually there is festival going on, so if you are hearing the dhol noise, I'm really sorry for that.
Can we know coefficient of expansion of any chemistry?
Coefficient of expansion of a compound.
Yes.
Let me see. If it's there, then we can.
Okay.
It still hasn't crossed it. So after some point, maybe after 200 degrees centigrade, it will cross it. So let's just search for a thymol boiling point. Boiling point of 232 degrees centigrade. Okay. So as you can see, till 200 degrees centigrade, there this both gives the energy of vapor and liquid. They are about to merge, like they will cross over. So somewhere around 232 degrees centigrade, this crossover will happen. That will be your boiling point. Okay. So this is how you can use this Gibbs-free energy tool analysis also to find the boiling point of a compound. Apart from that, what you were saying, that can we find coefficient of expansion?
Expansion. Yes.
Okay. Availability of pure component, constant pressure, heat capacity, this is ratio, heat capacity ratio, free energy, mass free energy, enthalpy. These are all enthalpies.
Yes.
Entropy, fugacity, free energy. Isentropic exponent, mass density for pure component, fugacity, PL, sonic velocity. Maybe it's not available. It's not a transport property, so it should not be here though.
Actually, the reason why I'm asking is
Hmm.
we use compressed liquids in our industry. So
Yeah.
what we do is we use a vaporizer and we expand it to change it to gas phase and use it in our reaction.
Yeah. But then coefficient of expansion, will it be changing with the conditions? It will remain same for the given component, right?
Yes.
So yeah.
Yeah, it may change. It may change with temperature.
Okay. Let's just search it. I mean, if it's there, it should be. So if you have any doubt, you can search here. Coefficient of expansion. Typical values of cubic expansion coefficient. So you have liquid thermal expansion scenario. Equation 4 is used. Probably not what you are looking here. Thermal expansion scenario. For piping. No, this is about thermal expansion.
Thermal expansion, something related to relieving devices,
Yes.
pressure relief device.
Yeah. Uh, so probably not. I will check it out. If it's there, I will let you know in next class. Okay.
Thank you.
So that was one thing. What else has been asked? We have been asked to do a PT envelope club. PT envelope plot. So you can select here. Here we have to provide either flow or mass fraction. So if you have any one compound, you can provide any value that will take it as 100% of that compound, and you can just do a simple run analysis. So what it will do, it will create a PT envelope for a thymol molecules. Then we can get a rough estimation of various temperatures, uh, temperature, pressure value, and sorry, boiling point at various pressure. Okay. Mhm. It's taking too long. Yeah. So this curve is ready. So as you can see, what we had found out was that at 1 atmosphere, uh, what we saw on the net internet was that 232 degree centigrade was the boiling point of thymol, and here you can see at 1 atmosphere around 231.9 degree centigrade has been calculated as the boiling point, so which is closer to obviously 232. So this envelope, what it will represent, that given temperature, if I am above this, what phase I will have, like liquid or vapor?
It's a vapor phase.
Will it be vapor or liquid? So if I am at 320 degrees centigrade, and if I increase the pressure of my system, I will move from vapor to liquid phase, right? So this is vapor fraction 1. At this point vapor fraction is 1, below which you will have a liquid. Am I correct, right?
Yes, yes.
Let's say even at 1 atmosphere also, uh, let's say at 2 atmosphere, you increase the system temperature, so you are in a right now you are in liquid phase, and once you cross the boiling point, then you will go into the vapor phase. So this bottom part is vapor phase and top part is a liquid phase. Okay. So this is the basic pure component property analysis that we can do. Now second problem, which is similar to this only, that here we want to again compute the density, specific heat capacity, Gibbs energy, and PT envelope for glycol molecule, which is 2-methoxy phenol molecule. Okay. So does any of you have a Aspen ready with you which can share your screen and do this analysis? You have it? Yeah, Santosh.
Yes.
Do you want to share your screen? So I guess
Yes.
so. Okay, so
Yes.
I will stop sharing my screen and then you can share it. So our compound is glycol. Uh, GUAIACOL.
COL.
हाँ. Yeah, it has added it. Method is not mentioned, so we will go with the unifact method. Press next. Hmm. You can select unifact method. Go next or run it. Yeah. So let's say we want to first CP, both for vapor and liquid phase. Select the unit. Um, Santosh, you are doing something as in from okay, yeah. Okay, so yeah. And you can do that also. You can add all the property in a one go and then run it. So we have CP rho gives free energy, and then we want to another is PT envelope that we want to compute.
Yes, yes.
Yeah. So so this is CP. Can you
Yes.
do a Gibbs free energy analysis and try to see the find the boiling point? No, go to the below. Not in the specification. Let's say pure. Select Gibbs free energy G. Just a minute. Let me search boiling point of glycol. GUIG. 205 degrees centigrade. So keep your temperature limit from 50 degrees centigrade to 250 degrees centigrade. Yeah. So
Yes.
yeah, can you
On
zoom?
the not.
So what is the temperature value at that point?
It's around 205.
205 degrees centigrade, and the that it's showing between 204 to 206 degrees centigrade. So we are in that range only. Okay. So at 1 atmosphere, this will be the boiling point of glycol.
Yes.
Similarly, you can also compute the PT envelope also, which will also help you to determine the phase boundary for vapor and liquid phase.
Yes.
So for PT envelope, you just have to, in the analysis itself, you don't have to select it from any property. Go to the analysis on the top right, on the top menu bar. Not here. So on the top menu at the end, you have this analysis tool, right? Go like click and then see PT envelope. Yes. So you have to provide a flow rate. So glycol flow, you can provide it as 1. So by providing 1, it will take it as a full component, as in only one component. If we have a mixture, then providing flow will be kind of providing a ratio. Okay. And then you can just do a run analysis. So you can see now we have PT envelope generated, so that separates the vapor and liquid phase, and then we can find out the what are the boiling points at various pressure conditions. Okay, so yeah, you can stop sharing your screen now. I will move forward with the next question. Thank you, Santosh. Okay, so this was the pure component analysis. Now we can also do binary component analysis. So if some of you who were with me in the first class uh, will remember, when I was showing the interface of this Aspen Plus, we had also calculated various TXY PXY plot, which are nothing but our binary property analysis. So let me first remove all this. The component. So question 3 says, using Pang-Robinson equation of state, obtain PT envelope for benzene toluene mixture and ethanol isobutane mixture for a different ratio of benzene toluene and ethanol mixture. So we have been provided 4 ratios. Okay. Similarly, what question 4 says, obtain TXY diagram for benzene toluene ethanol isobutane mixture at 1 atmosphere. Using ideal method and unified method. So these are question 3, 4, 5 uses same sort of a compound, just various properties that we have to calculate. Okay, so the first we will do for the benzene toluene. I will do for benzene toluene, and some of you can do it for ethanol isobutanol. Okay, let me delete this compound. And this. We have 12 questions. Okay, the method is specified as, one is Pang-Robinson, one time we have to use ideal, one time we have to use unified, and one time we have to use Pang-Robinson. Okay, so what I will do, I will add all. Ideal, okay, that has been added. The property. Not a good decision. It's taking too long actually. If it's okay, Shantosh, can you share your screen again? We can do simulation in your screen. I don't know, it's taking again too long to work in mine.
Shall I share my screen?
Yeah, you can share it. I will stop sharing my screen. So, so we have benzene toluene. Go next. You have added which method you have added?
I had not already given any method actually, just added the.
No, as in the property estimation method, I'm asking. So, can you scroll down slightly on the left panel? Scroll down. Specifications. Specifications. Go to specifications. Unifac is added. You can add Pang Robinson also. The Pang Robinson was there. Yeah, just slightly above it. Okay, that and ideal also. So if you will see, when you add it, add ideal. So if you will see below the selected method, in the selected methods folder, you can see others method have been added. Okay, so then we can interchange the method in between our calculation also. Okay, so what has been asked to us is, first using Pang Robinson equation of state, we have to find the PT envelope for benzene toluene mixture. So go to the analysis on the top right part. No, the last one, and go to PT envelope. So PT envelope. Now here we have been given 4 different composition. Benzene toluene as 1 gem 1, 1 gem 2, 1 gem 3 and 1 gem 4. So provide 1 for both, like equal ratio of benzene and toluene. Okay. We don't have to worry about the flow rate. This is just to provide a split. How much is benzene and how much is toluene. Okay. Then just run the analysis. So in the method part you have 2-3 options that will depend upon how the calculation has been done for this PT envelope calculation. We don't have to worry about it. So you can see for different pressure value, when we have this 1 gem 1 ratio, these are the PT envelopes present. Now this green line, which shows vapor fraction as 0, blue line vapor fraction as 1. So above the green line, what will happen? We will have a liquid phase. Below the blue line, we will have the vapor phase, and in between of them, we will have both vapor liquid equilibrium present. So if I am in between the green and blue curve, I will have both vapor and liquid in my system, which is in VLE part. Okay. Now
it shows that no isotope is there between benzene and toluene.
No azeotrope is there between benzene and toluene. No, anyway, yeah, benzene and toluene kind of are near to ideal solution, so they don't have any azeotrope. Okay, so now if you will go, so what you were trying to do, so there is a difference between PXY TXY plot. So PXY TXY are at particular, let's say if I am talking about PXY, that is at particular temperature, and I am looking the variation with a composition, while this PT envelope kind of gives you the phase bound of your mixture, where will be the complete liquid mixture present, where will be complete vapor mixture present. Okay, so there is a slight difference between what you want to do. Okay, so let's go into calculate PXY diagram. No, sorry, let's compute the PT envelope itself. So we have provided 1 gem 1 curve. Now can you go again to the PT envelope part? Not from here, go to home, click on home.
This one?
Just right side of the file, yeah. Home, just below that, yeah. Okay, now again go to PT envelope. Okay, so now provide benzene 1 and toluene 2. And run the analysis. Okay, so there has been some change, but we are not sure whether that change is how much change is happening. Okay, so what we can do, we can overlap two graphs. How we can do that? So on the top left you see the merge plot option, right? So when you will click on that, you have option to merge with the you have other graphs which are present in the system. So the previous graph, that was I think PT envelope 3, right? Can you just open it once to check? Open PT envelope 3. This is for our binary mixture, right? Okay. So merge PT envelope 4 and 3. Merge it with PT envelope 4. Not this one.
PT envelope 1 and 3.
It's okay. You can close it. It's fine if it this mixture one. It has combined CP and PT envelope, which is not needed. Yeah, close this one, this plot. Okay, you have PT envelope 3 and I think PT envelope 4 is also open. Yeah, so now go to merge, add PT envelope 3. Yes, select it. Okay, so now two are merged, but now there are axes are different. So what you can do, when you will right click on the graph, you can see the y-axis map, option of y-axis map.
Yes.
Go to that, and you have option of single y-axis. So when you will do that, it will merge both the y-axis and scale the graphs accordingly. Okay, so you can see there is slight difference between when we have benzene toluene as 1 1 mixture and benzene toluene as 1 2 mixture. Now here we forgot to label it, so we cannot tell which plot is which exactly. But for that, what you can do, you can also label it. Let's say you want go to PT envelope 3 curve or 4. Here what you can do, you can edit, double click on this plot. Now again double click here, so you can change it. So let's say this was for 4 is for 1 2, so you can write 1 2. Why input is showing red mark? Shailesh, input is showing red mark because he has already opened some other properties for which details has been not provided. So if you will see in the left hand side panel, pure 1, pure 2, pure 3. So he is using same previous simulation file to run this analysis, right? That's why it's showing input is incomplete. But it won't affect this property analysis. Okay. And this curve has gone, so what you can do is run the PT envelope 3 analysis again and generate it. Run it again.
Envelope 3, 1 is 1. 1 is
4 is 3 is 1 to 1, 4 is 1 to 2. Sorry.
Okay. Close this.
You can close it. Wasn't the PT envelope 3 1 to 2 part and 4 as see. So if you will see PT envelope 4, that is 1 to 2. So that was correct. I think the plot change the legend here, make it 1 to 2. Now go to PT envelope 3. You have to rerun it again because you have run it according to 1 2. So close this plot, go to 3, provide 1 1 again, and run the analysis. Now change the label as 1 1. Now you can combine it with PT envelope 4. and then we can see the difference. Okay, so you can see with 1 gem 2 mixture, the liquid phase boundary has shifted towards more higher pressure. Oh no, sorry, again we have to combine the both y-axis first, then we can compare it. So do right click, put a single y-axis and do it. Okay, now let's compare the 1 gem 2 and 1 gem 1. So what we can see when let's focus on the vapor fraction part, where vapor fraction is 1, which is blue curve for 1 gem 2, and green curve is for, sorry, no, pink is for 1 gem 1, vapor fraction 1. So you can see
pink and blue.
So you can see the PT envelope has shifted towards the lighter part when you have 1 gem 2 composition of both benzene and toluene. Okay, right? So this way we can understand the system's behavior with a different composition. So that was one example. Just a minute. Shailendra Kumar, for ethanol and isobutanol analysis is showing an error. What error it is? Can you speak it out? Or we can write out. Okay, I will do it. Now, Santosh, can you go to again home and binary analysis, and let's try to do plot TXY plot. What has happened? Okay, sorry. Shailesh Kumar, first let me discuss with Santosh and then you can share your screen. Okay. Now go to analysis and binary analysis. Okay, so binary analysis we have selected, yeah, obviously. Okay, so now we have various options in the analysis type. If you will go on the top part, no, again sorry, in the binary one, can you open binary one from your left panel itself? Input of binary one. So here you can see the analysis type is written by TXY is selected in a blue curve. So other options we have PXY, TXX. Okay, so let's say right now we have been asked to compute both TXY, PXY plot. So let's say first we will compute TXY. Component 1 and 2 are benzene and toluene. Basis is mole fraction of benzene. Okay, start point is 0 to 1. We can increase the number of intervals depending upon our requirement, and the by default pressure value selected as 1. Okay, so you can also add the second value. If you will 1.018 below that row, you can add the value of, let's say we want to study at 2 bar, so add the 2 bar. Okay, and run the analysis. So here you can see it has generated and merged both the plots of TXY diagram at 1 atmosphere and 2 bar. Okay, and what will happen when we will increase the pressure of our system? What will happen to TXY diagram? It will shift up or down?
Just shift up.
It will shift up because at higher pressure boiling point will go up, right? We will need more energy to vaporize the system, so that's why it has shifted up at the higher pressure conditions. Okay, so again, so this is the one analysis you can do. What else has been asked? Obtain TX, another is TXY. So from here only, now in this TXY plot you can also generate the YX diagram at given condition. So on the left hand side of your part, on the top left where TXY is mentioned, can you click on that? Is any other option coming here there?
No.
go to the binary input part, go to result. Okay, here you can see on the right hand side, you can see txy tx, so you can plot that different open the below. No, go back. Open the menu there, you have other options also. No, where you selected the txy plot, go right. So you can also plot yx for corresponding, click on that. You can also plot the yx diagram for a given select from selected txy or pxy plot. Okay, so that is also one thing. Now this has been generated via I think it's unifact method you have selected right now. Okay, again go to the binary plot input, in the calculation option. Okay, so right now method is selected, it's ideal method. You can change it and you can use any other method. So what we will do, first close all the plots. We will generate one plot with at one pressure with the ideal condition and one with the equation of state, and then we will compare the difference between ideal and equation of state. Okay, close everything. Now go to binary input, provide only delete this second pressure value. If you right click it, okay, it is deleted. Calculation option, go to calculation option. Right now first select ideal and run the analysis. No, you have to generate it. Go to binary analysis again, the input part of binary analysis, and run the analysis. Just change the label to ideal x, ideal y, legend, jo x and y, change it to ideal, like put ideal at the end. Now again go to binary input, and select let's say Peng-Robinson method. And run it. Now can you merge both the plots, the Peng-Robinson and the ideal condition plot? Oh, you have closed that. Oh, sorry. Yeah, one thing. No, it's not close, it's override. We have to generate a new binary property. So now from the analysis itself, on the top right corner, again click on binary. So now binary 6 is generated. So your binary 5 will be will have a different plot, and binary 6 will have a different plot. So now here select binary 5. Right now this is for Peng-Robinson. So binary 6 select for ideal condition, and then put ideal. And now you can merge both the plot to see what's the difference between ideal and equation of state condition. Can you merge the y-axis? So you can see there is slight difference at the lower section of benzene between the ideal model and the Peng-Robinson model. While overall at the higher section of benzene, curves are almost coinciding. Okay, so this is the one comparison between ideal and the equation of state condition. Similarly, we can do this comparison with experimental data that we will see next. So yeah, I guess this is done. I mean, you can also same thing, this pxy yx diagram we can do at uh, 110 20 atmosphere. I have given it in problem statement, so people can you guys can try it out later. Now I guess Shailendra, you had a doubt that with uh, ethanol and isobutanol it's not working, so can you share your screen so I can see it? uh, Thank you again, Santosh. You can stop sharing your screen. So yeah. What's the error? Negative temperature or pressure were obtained possibly due to singularity at mixture of critical point. Can I see your input specification? Go on top first. Let me see the compounds that you have selected. Ethanol and isobutanol. Okay. The method next. Peng-Robinson equation of state. Okay. Go next. What else you have? Result available with that. Can you reset your simulation? Click on reset. Now rerun it. Okay, one. Let me check in my simulation. So, had you started it in new simulation or you were utilizing same file? It could be that the previous stuff has been causing this issue.
Started with the new simulation.
You have used new simulation. Okay. So it could be some issue with the Peng-Robinson method or the mixture of ethanol isobutanol. Because I haven't tried out all the.
One more thing, sir.
Yes.
I have faced during the analysis of ternary mixtures.
Yes. Go ahead.
That if I change the sequence of the components, that tie lines number will change. Just
Tie
because
lines?
of I change the sequence of the components.
Numbers
It should not
change
be
as
like
in I think the orientation will change, else number of tie lines, the composition or other stuff should remain same.
So actually, with the Prabirkumar class, I just
Yes.
repeated the question and just changed the
Sequence, yeah.
series of the
Yeah, I
elements,
understood your
and
point.
the tie lines get changed.
As in how
So why this is happening, I don't know, but it should not be like that.
do you have that simulation ready or some photo with you?
No, sir, I can't help because in this afternoon I was doing the class.
Okay. Okay, let's try it out.
Time problem.
Yeah, we can try it and try it out. Just give me a minute, it's loading. Peng-Robinson equation of state. It's giving that negative temperature pressure obtained. Singularity at mixture critical point. Complete phase one cannot be generated. You can try to complete the envelope by specifying other vapor fraction branch. While generating 51 bubble point branch is not available due to convergence difficulty. Yeah, just give me a minute. My Aspen process is loading. Meanwhile, what we can do, we can proceed with the next part. After this question, the next question is for ternary diagram itself, where we have been asked. Just first, let me share my screen. You guys can see it, right? Okay. So you guys can see my screen, right?
Yes.
Huh. So question 6 is obtain the ternary diagram from acetic acid, MIBK, water mixture using NRTN method. Okay, and here we have to see whether isotopes are formed or not. Similarly, question 7 is also saying that we have to find the ternary diagram from ethylene glycol, MEK and water mixture. Okay, MIBK is this methyl isobutyl ketone, and MEK you might be knowing methyl ethyl ketone. Okay, yeah, it's running. So first, let me see the issue with the question number 5 and 6. What happened? It's battery died. So we have ethanol and isobutanol. Ethanol, isobutanol.
All isobutanol is running good for me with King Robinson.
Isobutanol is?
Ethanol, I tried it. No, it is running successful for me.
It's running successful, right? Yeah, so it could be that you might have not purged your previous simulation, Sailendra Kumar. Because of that, it might be showing an error. Let me just.
Shall I share my screen?
Just a minute. Yeah, you can share it. Actually, with recording, this Aspen Plus takes a load in my PC, so sometimes it becomes very slow. Yeah, you can share your screen. So can you start a fresh simulation so that Sailendra can understand? Start a new simulation. Close this one. File and new. If you want to save it, save it. Add ethanol. Isobutanol. No, you have to do find. Okay, go next and select Pang Robinson. It was just above it. Yeah. Yeah, results are available. So I don't think so. It could be that I will suggest to try it out again with a fresh simulation, Shailendra Kumar. Okay, because of that it might not be working. Yeah, it's working. So you guys can try it out with the ethanol butanol example. Again, it's about trying various things. Can you share your screen? Keep sharing your screen. We will do next example in your simulation only. So next question is finding a ternary diagram between acetic acid, water and MIBK. So add this compound. You can delete this compound. Right click on them and no, so right click and yeah, delete the row. It will delete that compound. Add water, acetic acid. You might have to search it. So there is a character limit between that. Write acetic acid. Water, and then we have this methyl isobutyl ketone. You can write MIBK, it might show up. Yeah. Okay, go next. So the method has been asked is to NRTL, so we have to select NRTL method. Go next. Next. Okay. Just delete this binary 1 and PT envelope part. So in the left hand side panel, right click on them. Right click on the binary one and you should be able to delete it. Yeah, delete that also. Now run the simulation. Okay, so now we want to see the ternary diagram. So can you go to ternary diagram on the top right part, on the top right corner? Yeah. So here we have different options. We will do ternary diagram calculation from Aspen plus ternary diagram. So continue to Aspen plus ternary diagram, last option. Okay, so now here we have selected 3 components and we have provided Whipple liquid equilibrium. Now number of tile lines you can change from 5 to let's say 10, so we might have more data points. Okay, and run the analysis. Yeah, so these are the number of tile lines, like the what should I say, the ternary diagram. This is how it will look. Can you move the legend to right? So in this legend you can see the last point is shown as the azeotrope. So on the legend there is one square block and you can find that square block at the mole fraction of MIBK 0.35. You can see there is a square block, so that is an azeotrope point. If you will go into the input part, this ternary diagram input part, go again, scroll down, again go down, go to input, and if you now you can see there are various tabs open. So if you will click on the azeotrope tab, so you can find the composition where this azeotrope is forming. So now here mole fraction of acetic acid is 0 and only water and MIBK mole fractions are given. So the azeotrope is forming, which is two-phase azeotrope, like between two components. which is water and MIBK. Okay, and as you can see from the ternary diagram itself.
This is isotopic temperature.
Yeah, this is the isotopic temperature, and from the ternary diagram plot itself, you can see that the point that has been shown as isotopic point is on the edge of the ternary diagram where two phase will lie. Okay. Now can
we
you go
shift this mass percent, or we should be able to see it in mole fraction?
No, generally it's with mole fraction, so that's why it doesn't allow you to change. And mass fraction again, I don't think so. The mole fraction is the correct approach here. Can you go to the ternary diagram?
Industry want to is we do it in a weight percentage.
Okay. I'm not sure the ternary diagram whether they are used with weight fraction, but probably. Okay. Can you go to the ternary diagram plot?
Or we should change this mole fraction to mass fraction.
Yeah. That if you have enough data, you can change it. Right now we haven't specified anything, right? We don't have any flow rate or anything. Now here you can see the envelope within the tile line, like the within the phase boundary. That will show the your the liquid equilibrium, where if we are in between any point, if you will recall the mass transfer phenomena, if we are in between the any point, we two phases will be separated out. Okay, one will be extract and one will be affiliate. Outside this phase envelope, we will have only single phase, like the mixture of our three components. Okay, and if you want to do liquid extraction, we should be within the phase envelope, right? Okay. Now coming back to the question of Shailendra, so can you change the order? What you do? Go to home. Again click on ternary diagram. Okay, continue to Aspen plus ternary diagram. So let's say we want to first put MIBK and put acetic acid later. Yeah, and just run the simulation with 10 tile lines. Okay, move it to right. So now Shailendra, what was your question here? What difference you are getting?
Water and MIBK.
No, that will be same. So if you will go to the ternary to input and see the azeotrope composition, can you go there? See the azeotrope composition.
What the same?
Yeah. Number of tile lines getting changed. So, just a minute. See, mole fraction of MIBK is 0.35 and mole fraction of water is 0.64 at 361 Kelvin. Can you go to the ternary one part? There it will be same. The azeotrope 0.35. It's exactly same. Number of tile lines getting changed. Number of tile line is a input parameter, so that we provide on our own, right? So right now we have provided 10. So you can see in the both the plots. Can you open the plot 2? So both the plots we have number of tile line as 10 only.
Only yes.
So that's it.
What we gave as in.
Sorry.
That's what. And is what we gave as in.
Yeah. So that's an input parameter. So it might be that you might have changed some input parameter while you were changing the sequence. Because of that, this difference would have come. Else it's same. Okay. Yeah. So questions 6 and 7 are both related to this. So we have done this acetic acid, MIBK and water mixture. Then next we can you guys can try it out, ethylene glycol, MEK and water. I will share this PPT, then you can check it out. Now next comes so what we did here was that we compared the if in the previous example, like benzene and toluene example, we compared the TXY diagram of various method, ideal method with Pang-Robinson method, or let's say Unifac method. But when we have an experimental data available with us, in that case, what we want to do, we want to select a method which follows the trend of experimental data, right? So we want to modify our method such that, so in that cases we will like to do some regression analysis or comparison with the experiment. So question number 8, uh, I will just share my screen for a few minutes to show you the question, then you can share it again, okay? So question number 8 is, obtain NIST data for benzene toluene mixture, generate PXY diagram and simulate data using various models and compare the diagram with available literature data obtained from NIST. Okay. So again we have to select the benzene toluene mixture. We will download some NIST data for PXY diagram of benzene toluene mixture and then compare which method corresponds well with the data of experimental data. Okay. Let me check if it's working. Okay, it's working. First, what I will do, I will select an ideal method. So here you can see in the top menu bar itself, so there are 3 options available. One is NIST, DCAMA and DIPPR. Okay, so these are the various data banks available in a way. So the Aspen Plus library, NIST. Sorry.
All these are literature values.
So NIST.
Yes.
Yeah. So if you will go into NIST website. So NIST is this National Institute of Standard and Technology, which has a compilation of various data present in it. So let's say if I want to search, like we were looking at the thymol molecule, right? So thymol molecule, NIST data. So you can see it has directed towards this part where I can get all the available data for thymol molecules. Okay. There are various references also available. Apart from that, the people who upload, so who do some, let's say, experimental values. So some of that experimental data are also available with this NIST website. Okay. Let me search here. Are they two different or same? This is thymol web. What is difference between this and this? Mask. So these are the basic data, like some of the basic data you will find in this PubChem or some other website also, where you can find the molecular structure of compounds, its various properties, the safety data sheet. Okay, you are from industry, right? So you must be using this MSDS of your compound. So that sort of a stuff can get from the other website also. But what this contains, the NIST data, it also contains some of the literature part. So you can see all the literature data which are present. Let's say Antoine equation parameter. and the experimental done. So there will be some experimental work done on this thymol molecule. So from that, within the temperature range of 337 to 500 Kelvin, 505 Kelvin, what will be the ABC value, which is fitted from the experimental observation. Similarly, enthalpy of sublimation, and same way there are other references available. Okay. So NIST is kind of a compilation of such data. So Aspen Plus has collaboration with this NIST, TD, which is Thermodata Engine, and DCAMA, which is the German Society of Chemical Laboratories. Okay, from there, data for various compounds can be availed. Okay, so what we will do, oh, results are available. Let's say I want to see the binary parameters for benzene and toluene mixture. Okay, so you can retrieve the pure component data, binary or ternary component data. Right now we have benzene and toluene, so I will do retrieve data. It will do search on the NIST server itself and then give you the available options. Okay, so in the binary part, right now what we want to do is we want to generate a PXY diagram. So we will look at the isobaric VLE data. Now you can see each of this data, it has some of the some data point value and is done by various researchers. So here you can see find the research paper where it has been published and the data has been taken from. Okay, so all the literature which has published such data are compiled here. Okay, so what we will do, we will select some value which has maximum data point, so that we can represent it better. I have written, I think data set 40 as a maximum data, 37, oh sorry, it's PXY, so we should look for isothermal, my mistake. Yeah, so let's say we are looking at PXY, so that will be at constant temperature. So isothermal data we will look. So in this various option, let's say I have selected that binary VLE 40. I find that this researcher's work is good and I want to follow this data. Okay, so with this PXY diagram is at 334 Kelvin. So we can save this data. When you will press the save, you will have an option to select other data set also. So right now I have selected from vapor liquid equilibrium 14 number, so that has been only selected. I can add other data also. When you will do OK, this data will be added, and you can see in the data section here this data has been created, and you can find the other information about the data. Okay, from here you can plot the data itself like TXY diagram. Sorry, not TXY, since it's a isothermal data, we want to do PXY diagram. So this is the PXY diagram from experiment at 334 Kelvin. Okay, now I want to see for benzene toluene mixture what PXY value I will get from ideal method, unifact method, or any other method of our liking, and we want to compare that which method is more closer to the experimental value. Okay, is my screen visible to you or is it stuck? Hello?
It is visible.
Is it visible then? Oh, is there some issue with the recording? Just give me a minute. I guess recording is stopped at some point. Just give me a minute. I think it's issue with the recording. Huh. Sorry, the recording was stuck at some point. Anyway, so this data we have generated pxy at 334 Kelvin. Now coming back to binary data analysis, I want to generate txy, not txy, sorry, pxy at 334. So this data is at 334 Kelvin. Okay, so I want to generate another pxy plot from the ideal method and want to compare it with the experimental data. So run the analysis. Not again. Just a minute. It's taking too long. Let me just quickly see what other example I had planned. So I had taken out multiple questions, but I was not sure how much we will go. So rest of the question we will do it next time. Anyway, we are just close to closing the session. So this was the
question number 10. If you don't mind.
Sorry.
Question number 10. It is what should we do? Develop user-defined molecule of vanillin. Molecule.
You want to do this question, you are saying?
Yes. If
okay.
you don't mind, please.
Yeah. I was thinking that only. So anyway, for first, let me finish this question. So let's say we want to compare this with experimental data. This is the ideal method, and I want to say merge the plot. Why we cannot merge it? So again, you can see at the let me single by. Okay, what happened? Both are pxy, right? Maybe I made some mistake. Okay, pressure values are different. So our experimental data.
Temperature values.
Sorry. No. So experimental data, pxy data is on with Newton per meter square. So here, change pressure value to Newton per meter square. Okay. Now we can merge the plot. So you can see the ideal method and experiment, they are almost near to each other. Okay, obviously there will be slight difference, but if you will account for the percentage error between the ideal and experimental data, you will get some slightly less values, like lower percentage. Why this is happening? I mean, ideal method is matching with the experimental data for benzene and toluene? Can any of you guess what is happening here? So benzene and toluene mixture is it close to ideal condition or away from the ideal condition?
It's closer.
It's closer to the ideal condition. That's why these datas are matching. So even if you will, when you will try the other methods, so right now we have just selected the ideal method. Let's say you are trying the Unifec or NRT or any other method. In that case also you will find that that method data is matching with very close to the experimental. But for this second part, like question 9, I will recommend you guys to try it out. For the ethanol water mixture, what will happen is that the experimental data that you are getting will not match with your ideal condition, since the ethanol water is not an ideal mixture. Okay. So that's why there you will get a difference, and then you can try out various methods to see which method closely resembles the experimental value. Okay. So this was the first part, and I will do this last question number 10. The main reason is to do, like, your assignment also includes some similar similar question, right? The current week assignment. So that should help you to solve this assignment, and rest of the data. And so rest, then we have I had planned out some regression part, how to do data regression, so that we will do it next time. We will try to complete it next time. Okay. So this example, so right now we are doing property analysis of component which are known to Aspen Plus. Okay. But let's say when we don't have the data available itself, let me clean this all stuff. Let's say when we have some new compound, or the compound for which the methods are not developed too much. In that case, it becomes important to find the properties of such compounds. Okay. So then how to compute basic, like, properties such as critical temperature, critical pressure of such compound. For that we can use the Aspen Plus tool to find to do some basic property estimation. So right now what we will do, we will define one molecule, vanillin, through molecular editor. So first, if you will search the vanillin molecule, okay. So this is how vanillin molecule looks like. Okay, it's an organic compound with a phenolic aldehyde group. Okay. It might be available, but we are saying it, we don't know it. So you can give some compound name. Let's say I want to say it compound V for vanillin. Okay. And I'm putting its name as vanillin. Go to next. Alias exists. Okay, sorry, alias is already there, so let me just say it as when and do next, because this compound is already present, but we just want to try it out.
Yes.
Alias of this what happened? Maybe again you can help me out with this situation. So can you share your screen again, Santosh? Yeah.
Yes.
Yeah. Thank you. During rates and declared tally. Just can you do next? Are you getting same error? Okay. Just instead write comp v again. Write same as component ID. The alias, sorry. So component ID, you write it as comp dash v. Write alias same as comp v. Go next. Okay, now here we have option that either I can draw the molecule or I can provide its mole file. So what we will do, if you will search on the web, can you search vanillin on the web? Yeah. So from here we know its like molecular structure, how it looks like, but we can also find the mole file. Mole file is nothing but the essentially a structure file. So vanillin mole mol file, no, just mol file. Okay. Can you open this NIH data? Scroll down in the, it should have, no, not molecular weight. Go down again.
Structure.
I need a structure data like mole file. So go to structure here. Can you go download the coordinates? Do that. No, slightly go up. You can see download coordinates. They don't have mole file. They don't have mole file. So go back to the Google search. The third website has SDF or mole file. Can you go there? So here that download structure data file. Can you just open it in Notepad? This is SDF file, probably might not work. Go down. Okay, we can try it out if it works or not. So this is like kind of a coordinate. So here the coordinates are provided and the connection between molecule is given. So go to the Aspen Plus window. Now click on draw or import edit structure. Right. So here you can see on the top left corner there is this file option, file icon. And select the recently downloaded file. If it will go, we can use it, or else we will draw it if we don't find it. Can you do all file, the filter? No, in your Aspen Plus, go down, put your cursor above open. Smile is also, you can provide smile also. Okay, so smile is also another file type. Can you search smile for thymol, sorry, not vanillin. I mean, it's not, it won't take SDF file, so it's not showing here.
Yes. It's not taking this.
So either we can draw it, or just quickly search it if we can find it, or we can draw it here. Go to browser and see on some other website if we can download it. Go to chemical book, probably it will have a data. Yeah. So no, go up. It has mole file. Yeah. Can you go slightly down? Scroll down. You see that 121 just above it. That is mole file.
Yes.
Now try to import it. File, import. Okay, so structure has been added. Now you can close this window. Okay, now we can add other available data set also. So what have we have? So we have boiling point as 285 degree centigrade, specific density as 1.06, and molecule weight is 152.15. Okay, rest of the data we don't have, so we will just press next. Okay, now there are two options. One is evaluate using NIST TDA data. So what it will do, it will look for the NIST data set if we, and try to find the compound which matches with this description and take out its data. So if you will do evaluate now, click on evaluate now. Yeah, do OK. So it will search the NIST library, and from there it will take out the vanillin, it will identify vanillin and take out the its property. Okay. So you can see what it has done. It has gone through NIST website and find out all the data for given entered compound. And we can compare this data with data available in the literature also if you want to do it. Right now we won't do it. Okay, so this is one way of finding
compressibility factor, density. Okay.
Yeah. Okay. So
if
this
you don't have mole file, then you need to draw the structure of it.
If you don't have a mole file, we have to draw the structure. So this is the one way, but we want to, let's say, since the vanillin was already available, that's why it found out from the NIST data. But if we don't have it, then it won't find it. So in that case, we have to evaluate it. So go to the components again. Here, now again click on user define. Go next. Next. Now we can use estimate using Aspen property simulation. Why it's not clicking it? Oh, I think because we evaluated from NIST. Can you close this window? Scroll down on your the left hand side panel. Scroll it down. Scroll down. Further, go down. There should be this estimation. So click on estimation. Click that folder, the small triangle. Yeah. And input. Click on input. I think it doesn't have any result. TD pure data. Can you search for TD pure result? I want to delete that so that we can do the other analysis.
TD result.
Go. If it's not there, then go again to the compound. Okay, I will show you how to. Go to the component. Sorry. Okay, what you can do on the left hand side, you see the molecule structure part on the left panel. Just above it. Go. Can you click that small triangle, and we have compound V. Okay, so here what you can see, go to structure and functional group. Okay, there are compound V data also available. Now from here only I just want to do again method estimation. Go to, just a minute, what was can you go again to the specification part and edit the molecule? Compound, component specification, user define. Next. Do next. Next. again. Estimate, why it's not showing up? Click 1 to 5 to enter additional data. Or you just reset the simulation and start the new one. Close the simulation and start the new one. I think it's not allowing us because we have computed data from TD. Close the simulation and start a new one. Yes. Now go to user define, create compound V. Import the mole file. Now boiling point is 285 degrees centigrade. Density is 1.06 and molecule weight is 152.15. 1.06. Do next. So previously we generated data using NIST. Now we want to do estimate using Aspen Plus. Oh, just we have to do finish. Sorry. Okay, my mistake. It was there previously also. Okay, sorry, my mistake. Now do okay. Go down, scroll down. Go to estimation. Click on that small triangle. See results. Oh, sorry, we have not selected method yet. Can you select any method? Let's provide NRTL right now. Now again run the simulation. See the results. So results are here. So it has calculated TC, heat of vaporization, for pure component. Click on T dependent part. On the top tab, there. So there are two values in pure component. In T dependent, click there. You can see the heat of vaporization and liquid thermal conductivity. Okay, but these are the value, estimated value, and it has mentioned the units and some method. Okay, so on the right hand side you can see there is one method mentioned, Viter, STO and something. Okay, same for go to pure component. There also it has calculated this via some method. Now what these methods are? So actually what it does is, when we don't know, when we don't have any experimental data for any compound, or that compound is very new to us, in that such cases we use this group contribution method. If you guys have heard it, so there are this Joubek group method, Marino-Gani group contribution method. So what does this group contribution method does? It identifies the various functional group and what kind of property. So it has, what should I say, various coefficient and constant assigned with each functional group. So let's say your compound, it has one alcohol group, one amine group. So it will have its own equation. So to find its boiling point, so based on the alcohol group will contribute to some property, amine group will contribute to some property. So this group contribution method has such equations, and based on your compound, what groups are present, what atoms are present, for each group there are coefficients defined which are fitted off based on the experimental data. So what it has done is, it has used this simple method which has tried to identify various functional group or atoms present in the system, and based on that it has calculated the TC value. Now can you scroll down again onto the structure part? go up. So when we select the compound, can you go there? Go up again. Now in molecule structure, go to molecule structure, open it, compound V. You can see structural and functional group. Can you click that? In the functional group, there is this method option, the right tab. Can you click that? So in the scroll down method, you can see these are all the group contribution methods. The Joback group method, there are other methods also. Each group method, it has functional group type also, and then group. In the functional group type, click in the group, can you go down? So see, various groups are already predefined. So depending upon your compound, you can define such pre-groups, and what it will do, it will have values assigned with each group, and it will try to solve such set of equations which are what should I say, specific to this group contribution
Yes.
method, and it will calculate the property. But right now what it is doing, it is giving very less properties. One reason for that is right now we have just provided the structure, but it has not completed the structure part. So if you will click on the calculate bond option on the left side, calculate bond option, click it. Go to general. I think it should have generated. So yeah, here now the bonded network of your structure is also created. Okay. Now when you will do run analysis, run the thing. Now go to estimation and the result of estimation. Go down, the estimate. So pure component, click on that. And so you can see now there are multiple values are there. So previously there were only few things present, because there the structured data was incomplete. Because of that, this group contribution method were not able to assign the data. But right now we have PC, critical pressure, critical volume, critical compressibility factor, then the heat capacity at 300 Kelvin, 500 Kelvin. Okay. Now you have this eccentricity factor, even T dependent parameter. If you will click there, on the top part, click there. So now we have ideal gas, heat capacity, vapor pressure. Go down, liquid viscosity. So multiple properties are calculated. How it happened? Because we provided the connectivity. Now when we draw the structure on our own, we just give it that these are the atoms present, but we don't explicitly specify what are the bonds here. So in that case, you have to do this calculate bond option so that it gets the complete structure idea. And from when we import it from mole file has a connection between each atom, so it should ideally identify such things. But for this case, it hasn't identified. Because of that, it was not calculating all the properties. But with the complete connection provided, group contribution method will be useful to compute such TCPC value. Okay. So in your assignment, I think similar structure is given where you have to draw the structure. And if you don't get all the properties, probably because the connections are not created. So in that case, you have to create the bonds, and then when you will run the analysis, you will get other properties also. Okay, that is one thing. But so this was the idea, like when we have some new compound for which we don't have the data, then we can use this estimation method to calculate the property. And now you can stop sharing your screen. That's fine. Thank you. But why this estimation method is needed anyway? You might be wondering, right? That
Sometimes we need to identify properties of unknown molecules.
Yeah. So anyway, like what is important? TCPC, such things are important. But why these are important? So see, all the property methods which calculates this. Let's say if I talk about equation of state. So equation of state calculates various properties. But what are the input parameters needed for equation of state calculation? Let's say I am calculating methane property by equation of state. In that case, there will be some input parameter which I am providing, and such input parameters, if you will recall, that are your TCPC conditions, okay, to critical temperature pressure value. Based on that, the uh, constants which are used in your equation of states are calculated. So if I share with my screen with you, let's just quickly see one example of equation of state from Google itself. Let's see, I'm saying Bang Robin Robinson equation state. So these are the equation of states: classical, virial equation, BWR, okay. So here you can see each of this has some constant associated with it, this A0, B0, and how this constant are calculated based on your TCPC value. Even in, if you will recall your thermodynamics classes, when we were calculating this uh, SRK or Peng Robinson equation of state, or this Van der Waal equation of state, we will, this A and B parameter that are associated with C TCPC values of your compound. So this basic information is needed in order to find other properties from the equation of state, like the VLE data, vapor liquid equilibrium data. So from equation of state we get P set versus temperature profile, P set L and P set versus 1 by T plot, we get rho versus T, which are useful for our column designs, okay. But in order to do that, TCPC data is needed, and that data can come from this group contribution method. Now each of these has some sort of approximation in it. That group contribution method itself works on some assumptions, and it tries to find the functional group and assign values according to functional group present in your compound. So there is some estimation there, and from there you move to your equation of state method. Now different equation of state method has some advantage, disadvantage kind of a thing, okay. So there you get a different property. So there is some trade-off that you have to take care of in computing the properties. But this is the purpose of, you know, using finding this estimation of properties for unknown compound. We are not just doing for kind of a learning perspective. Obviously it's learning perspective, but I want to show you how it is useful, okay. So that is it from my side. Rest of the question we will do from the next class onward. That is basically related to the regression part, and that's it, I think. Then after that we will move forward with some of the example questions, like case studies that we will try to study in each class, okay. So do any of you have any doubt? Yes,
Thank you so much.
yeah, welcome. Do you have any other doubt, or should I stop? Okay, so I will stop the recording. You guys can leave.